Welcome to your crash course on vector addition for first year physics, aka the Pythagorean Theorem and the arctangent function. When we first defined displacement, we made a big deal that it was different than the distance you actually went. If you're a field biologist tracking some rare species of moose, and you see that the moose wandered off from where you intended to find it, 4 kilometers to the north, an additional 3 kilometers west, then you probably want to cut across and intercept it before its transmitter goes out of range. The moose's final displacement is going to be somewhere over here. Let's put numbers on this and find the moose's final displacement. Well, that's straightforward. This is clearly a right triangle, and if we want the length of the hypotenuse, good old Pythagoras will say this squared plus this squared is going to be that squared. Type that puppy into your calculator. Be very glad it's a 3, 4, 5 right triangle. Life is good. You just have to go 5 kilometers into the wilderness, and there you will find your moose. Wait a minute. Let's run through that again. You're going to go 5 kilometers into the wilderness with no compass, no flashlight, no water bottle, no bear spray, no idea where you're going. No, we are not done yet. 5 kilometers may be the distance from where you started to where you want to end up, but it's not the displacement. We're not done yet. If you're going hiking in the wilderness, you will need to know your direction. There are 3 ways of dealing with direction. 1 from math class, which is where we're going to start, and 2 with actual bearings like pilots and navigators. We're going to name the angle we want theta. It's a good name for angle. All angles named theta. The question is, which angle do we want? Do we want this one here, because it's right and nicely nested in our triangle? Or do we want this one here, because although it's not exactly what we'd call in our triangle, it is the reference angle relative to one of the axes. Turns out if we want formulas we can use in class, this one here is going to be the one to go with. Rule for physics class: if you want to use formulas, then always measure angles from the x-axis. Always measure angles from the x-axis. Even if it's outside the triangle, that's okay. We'll go with it. Just this is the one that's going to be our standard for which all our formulas can follow. Well, this theta over here isn't so bad. If we were using this angle here, phi, the nested one, we'd say, hey, take a look. Opposite over adjacent, that's the tangent. That means the tangent is x over y, and then we can find the angle using the arctangent. My point is that the same is true by good old similar triangles out here. There's a nice similar triangle here with an opposite of 4 and an adjacent of 3. Oh, Mrs. Eliezer, we just found the hypotenuse. Can't we use a sine opposite over hypotenuse, or a cosine? It's right here along the x-axis. It's 3 and 5. Wouldn't we get the same answer if we use a sine or a cosine? Yes, totally. Go for broke. If you want to use this angle here nested with the vertical, fine, use it. Use phi, you'll get the right answer. You want to use a sine or a cosine? Get the right answer too. Here's why I always go for the tangent. See this? This was not given in the problem. This I calculated using my own calculator or my own head if it was a 3, 4, 5 triangle. These numbers here, they came from the problem. They were printed in black soy ink on white paper, or in the case of COVID-19 2020, they were printed on black pixels on a white screen. These numbers are reliable. If I screwed up something and my calculator was in the wrong mode when I calculated the hypotenuse, I still want to have my bearings right. If I tromp through the woods in the right direction, maybe I'll meet the moose 1 or 2 kilometers earlier than possible, or maybe I'll have to walk for an extra quarter of a mile or so before I find it. Hey, maybe the moose wandered off, or maybe my calculation was wrong. But I definitely want the direction to be right, so I always want the direction that's given in the problem, and that's the one that looks like this. If you want to know where you're going, you want the Pythagorean Theorem and the arctangent on this angle out here from the x-axis. Bust out your calculator, find that angle, and then we'll talk. Pause the video, press play when you're ready. All right, theta is the arctangent of 4 over 3. That's 53.1 degrees, right? Not quite. Remember, direction. 4 is up. That's north. 3 is across to the left. That's west. West, guys, is negative. Check your quadrant. You are in the second quadrant, and that is why when your calculator gives you the answer of negative 53.1 degrees, you're going to say, wait a minute, that's not true. Negative 53.1 degrees is over here in the fourth quadrant. We are not over here. Negative 53.1 degrees is tracking a moose that's going south, and your readings clearly indicate that this moose is going north. What you have here is the reference angle. This is 53.1 degrees measured from the x-axis. Your calculator cannot do an inverse tangent for all 4 quadrants because that operation would fail the vertical line test. Your calculator will give you a positive answer. If you're going northeast, you're good, you're done. Your calculator will give you a negative answer. If you're going southeasterly, you're done. But if you're going anywhere in west, your calculator will lie like a rug because west is too much for its little electronic brains. And that's why you're glad you drew a picture. You can clearly see that this is something less 53.1, and specifically, that something is 180 degrees. Take 180 degrees, back up 53.1 degrees, exactly as your drawing told you to, and there you will be. Of about 127 degrees or so. This is what I mean when I say a proper math class angle. Proper meaning that it's in the proper quadrant. You can tell just by looking that a moose that's wandering northwest ought to be found in the second quadrant at an angle between 90 and 180. Use your eyes. If you know you're in the second quadrant, take what the calculator gives you and add 180 to the answer. Now, bearings from the compass. Here's our compass. North, east, south, west. Bearings start with a cardinal angle. Go to your diagonal, use your reference angle, and find the nearest axis. I guarantee there is one. And go from there. Which axis is this angle here touching? Clearly it's not south. Clearly it's not east. We're over here on the western axis. So as far as these bearings are concerned, the first thing we're going to have is west, because we're starting west. From the west, we rotate a certain number of degrees this way until we get our vector going in the proper direction. How many degrees is that? We just found that. That is 53.1 degrees. Which axis are we rotating toward? It's the one up here, the north. So our final bearing, if we're doing this pilot fashion or navigator fashion, would be west 51 degrees north. Equally accurate would be to use phi over here to start on the north, go from the north this way until you get your vector pointed in the correct direction as before, and that would be north. Let's see, arctangent of 3 over 4. Arctangent of 3 over 4 is 36.9 degrees. That would be north 36.9 degrees west. Those are congruent bearings. They put you to the same direction and the same direction as 127 degrees going out into the second quadrant in proper math class angle. There are your 3 ways to state the answer. If you're going into the woods, bring your compass and your cell phone and your water bottle and your bug spray and your safety gear. Orient your compass toward the north, then turn from the north 36.9 degrees toward the west. Try not to crash into any trees and step into any rivers. And after 5 kilometers, you should find that moose. Good for you. Another example, let's try relative velocity. You're in a ship. If you watch a leaf on the water, you'll see that the current pulls the leaf along, and the leaf has no engines at all. If you're in a boat, you're riding on this current. What it does, you do too. And there's what your engine does. Riding on a boat, you not only have to contend with your engine speed, you have to contend with what the current is doing also. So if you're trying to go 183 meters per second this way in your speedy little speedboat, but the current in the river you're trying to cross is flowing at a whopping 100 meters per second the other way. Yeah, I know. I'm trying to get a nice hypotenuse here. You are not going to move straight across like you. As you try to go across, the current will sweep you downstream like this. And it's a very straightforward vector addition. Pause the video and find the final velocity relative to the ground that you're going to get between your engine speed and the current drift. Press play to check your work. Remember to make sure theta is measured from the x-axis. You want not final speed, but final velocity, magnitude, and direction. Ready? Here we go. Pythagorean Theorem, square root of 183 meters per second squared plus 100 meters per second squared will give you about 200 meters per second, really closer to 208 meters per second. There's your magnitude. Your direction, theta, as measured from the x-axis, is going to be the arctangent of your Vy over Vx. That's 100. Oh, wait, no, it's not. That's negative 100 because you're going down over 183 east. That's okay. And that's going to be negative 0.5 radians or negative 28.6 degrees. Stop. Quadrant check. Negative, that's fourth quadrant, that's southeasterly. Are we going southeasterly? Yes, we are. Problem is solved. If you want that in bearings, here we are on the eastern axis. That's going to be east, 28.6 degrees south. Or if you want to live dangerously, you can do 61.4 degrees east. Problem solved.